Hi, welcome back. So we're in chapter 5, prediction by probability. In this chapter, we're going to be exploring a number of outlines. First of all, we're going to be looking at introduction to probability, then univariate concept of probability, followed by bivariate concept of probability, and finally multivariate concept of probability. Let's go ahead and explore the first outline. Now, randomness and uncertainty exist in our daily lives as well as in every discipline in science, engineering, technology. And I think probability theory is a mathematical framework that allows us to describe and analyze random phenomena. So you could see now the idea of random is somehow related to the word of probability. And by the random phenomena, I mean the event or the experiment whose outcome we can't really predict with certainty. Let's think more carefully about what we mean with the term of randomness and also the term of probability in the context of one of the simplest possible random experiments, say flipping a coin. Possible outcome could be a head or a tail. One way to think of randomness, giving this context of example, is that the way we express what we don't know. Perhaps if we knew more, say, about the force I flipped the coin with, the initial orientation of the coin, say the impact point between my finger and the coin, the turbulence in the air, the surface smoothness on the table, the material characteristic of the coin table, and so on, we would be able then definitely to say whether the coin would come up with a head or a tail. But the case is actually we cannot really predict the outcome of flipping that coin because we don't really have enough information. We don't really know, or we don't have that kind of knowledge to tell us exactly. So that's why we try to give a probable and numerical presentation on each one of these outcomes. Now, since the coin is fair, if we assume that there is no bias for either the head to happen or the tail to happen, the probability that it will come up with head is going to be 50% and the other will be 50 anyway. So it have to sum up to 1. So to put that in a much more context, maybe we could look at a probability type, if you will. Well, the first one, you could look at it from a classical way. The second one, maybe we could look at it from empirical way. And the last one, we could look at it from a subjective point of view. Now, what do we mean exactly with a classical way? It's the way we count things. Based on counting mechanism. I got 2 outcomes, so I can guess half here and half there. Empirical perspective, that means based on a relative frequency of a historical data. So I look at the history and then I can decide. And the last one based on a subjective or a kind of a feeling. Most likely can be accurate most of the time, like by experience, say, well, I think it's going to be, we call it an educated guess. But anyway, I think most of the time we're going to rely on the understanding of a classical and empirical because one of them related to the history, the other one related to much more a mathematical foundation of understanding. Where subjective is not bad things to happen, most of the time we can look based on a good experience of intuition, if you can say, then we can decide. So basically what we are going to do, we will be starting with the univariate concept of understanding probability, and then we will follow the branch on this map as a guideline anyway. So let's go ahead first of all and try to explore what we really need to know about probability as a fundamental knowledge that we have to be ready before we actually get into much more detail, and some of those models are available for us. Start with the idea of reviewing what's so-called the set theory. Now, probability theory uses the language of set in general, and as you will see later, probability is defined and calculated for sets. Here we are going to actually briefly review some of the basic concepts from set theory, which we are going to be using actually as we go along in this chapter. First, we're going to discuss like the set notations, the definitions, maybe the operations such as intersections and union, and then we will also introduce accountable and uncountable sets, and finally maybe we will have a quick briefly discussion on something called the functions. First of all, let's go ahead and see what does set actually mean. It's a collection of some items or element, and we often use the capital letter to denote that. Now, to define a set, we can simply list all the elements in a curly brackets. So in this case, A is known as a set, 3 and 2 are known as the element. Now, the order of the element in this set, it's not really matter. We have defined N as actually a set that contain all the natural numbers such as 1, 2, and also we have explored integer numbers. This is a set of all real numbers such that x larger than equal to 1, but it's less than or equal to 2. It's a set of all real numbers such that x is larger than 1, but it is less than 2. Maybe in set theory, these are something quite a bit important. And that's why we led to the idea of stating the property satisfied by the element in that set. For example, I could say element of x such that satisfy maybe a certain condition to be element of A. Say, for example, I get set C contain x such that x is a subset of integer numbers larger than equal to -2, less than, say, for example, the value of 10. Then C is actually equal to -2, -1, all the way up to value of 9. All right, so A is a subset of B if every element of A is also element of B. So it is a sample indicate that A is a subset of B. Based on this element here that we see in both set, we could come to the conclusion to say, well, that means E is a subset of C. Also, you could look at the idea of two sets are equal if they have the exact same element. So this is our basic idea on reviewing the meaning of subset and their intuition anyway. Maybe next we can also discuss the Venn diagram. Now basically the Venn diagram is very useful in visualizing relation between sets. Now in a Venn diagram, any set is depicted by a closed region. In this case, we could say that this S here, I mean the square one, we call it the universal set, and A is actually a subset of that universal. You can make this quite a bit much more intuitive by actually drawing another set inside A. We call it B. B is a subset of A, and both of them are actually belong to the universal set of S. So let's look at some of the operations here. The first operation, we call it maybe the union operation. The union of two sets is a set contain all elements that are in A or in B, possibly to be in both. From Venn diagram perspective, you can depict that A UDB, it indicates all these actually shaded area. The previous set here 2 was actually somewhere around here inside this intersect, but 3, for example, was only in B, whereby 1 was only in A. If this is similar, it can be defined actually union of 3 or more set. It doesn't matter really. It indicates by using the upper arc like this, union will say I is equal 1 to N. Another type of operation we call the intersection operation. A intersect with B consists of all the elements that are both in A and, I think this is the key word. So previously we saw or, now we are seeing with the intersection related to the and B. The intersect between them, it should talking about this shaded area here. Of course, this also can be formed for as many sets. So just indicate again, I is from 1 to N and then AI. Maybe another operation that you have to be familiar with relates something called the complement. It's the set of all elements that are in the universal set as but are not in A. It is in here in this white shaded area, but it isn't in A. Also, you get another operation called difference or subtractions. Consists of all elements that are in A but not in B. A minus B is this one here. Another type which we call mutually exclusive or disjoint. Their intersection is an empty set. You could easily say, well, A, B, and C are mutually exclusive or disjoint because they don't have any joint elements. There are some theorem kind of operation law that you might also want to be familiar with. One of them so-called the De Morgan's law. The complement of this uni, it's exactly equal to complement of A uni with a complement of 2 all the way to the N. The next one called the distributive law. You got set A intersect with the uni between B and C that is exactly equal A intersect B uni with the A intersect with the C. Next one, maybe it's quite a bit interesting that you have to be quite a bit familiar when calling the Cartesian product, written as A cross B, is a set that contain ordered pairs. So we're talking about pairs here. Take every element of this and distribute it to be paired with the next one. It's quite obvious that A cross B is not going to be equal to B cross A. You have two finite sets like A and B. A that has m number of elements, B has n elements, then A cross B has m by n elements. This rule is called a multiplication principle, and it is really very useful in counting the numbers of elements set. This denotes the length or the total number of elements. Maybe also we want to talk about something called the cardinality, countable and uncountable set. If you have A, we could say the cardinality of A is just equal 1, 2, 3, 4, 5. So it's equal to 5. Very useful rule called the inclusion-exclusion principle. Cardinality of A uni B equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersect B. Maybe I have an interesting example. The guys who are in a white shirt, 4 of them are wearing green shoes, and the guys who are in a red shirt, 3 of them are wearing green shoes. White shirt or red shirt or green shoes are actually 21. This is the total number. The question is, how many people actually have green shoes? The information here have to be understood first before we answer the question. So how can we approach this problem? First of all, let's create set. We can say we have set W and we have set R and we have set G. So we have 3 sets here. According to the summary, we know that cardinality of W is equal 10. Cardinality of R is equal 8. Cardinality of W intersect with G is 4. R intersect with G is 3. W uni R uni G is equal 21. These are the information are given to us. It is reasonable to assume that the W and the R disjoint with 0. And then we can apply what we were talking about, the inclusion-exclusion principle. Well, W uni R uni G, green shoes, equal 21, right? Which is actually equal, can be written in a different form. That is W plus the red plus the green minus the intersect. Take one with this, and this with this. Finally, plus intersect between all of them. Let's now substitute values here. If you reorganize everything here, that will lead you to 10, the actual number of people who were in green shoes. If you like also to use the Venn diagram perspective, if you look at this region, let's call it X region here. It says that 21 is actually equal 10 plus 8 plus X. What we want the cardinality of G, I mean the total number. So G is actually equal 4 plus this X value, which is just we get 3 plus 3. Which is equal to 10. The last thing, the function concept A is mapping to B. In other words, to look at it as you have a domain here, which is mapping through this function f to a codomain, we call it, precisely interested with a range, specific range called the f of x. Now, the best example I could say, f of x is equal to x squared. X is in real number such that x is larger than or equal to 0. The output of a function always belong to the codomains. However, not all values in the codomain are always covered by that function. In this example, is mapping to R, but the function value is always positive number. Now, we are ready maybe to start details on the technicality of using probability as a tool for prediction. That's exactly what we're going to do next. I will see you then.